So meta-analysis, a lot of people equate it with systematic reviews, but it's actually different. Not all systematic reviews would have a meta-analysis, and meta-analysis is really a component of a systematic review where you have enough data to combine them statistically. And here are two classic definitions for meta-analysis. It is the statistical analysis of a large collection of analysis results from individual studies for the purpose of integrating the findings. Or alternatively, a statistical analysis which combines the results of several independent studies considered by the analyst to be combinable. Personally, I like the second definition better because you have to decide, as a systematic reviewer, whether the studies are similar enough, such that you can combine them in your meta-analysis. Most meta-analysis are presented in forest plot. And here is one example of a forest plot. Here we have 5 studies. And each line and the square in the center represent the results from one study. And the size of the square is proportional to the weight that each study is taken in the meta-analysis. The larger the square, the more weight the study is taking. And we also have the 2 sticks around the square which shows you the confidence interval for each study. If you look down on the plot, you will see a diamond, a blue diamond. That's where the meta-analytical effect lies and where the point estimate is, and the confidence interval for the meta-analysis. Depending on the measure of association you're going to use, you may have different scale on the x-axis. For example, here we're using risk ratio. A risk ratio of 1 is the now effect. And you can label your figure such that, if the diamond lies on the left of the line of no effect, it favors the treatment. Or if the diamond lies to the right-hand side of the line of no effect, it favors the control. So you can actually show the direction of effect on the same plot. Meta-analysis provides us statistical methods for answering what is the direction of effect or association. What is the size of effect? And is the effect consistent across studies? You may also want to ask the question, what is the strength of evidence for the effect? Assessment of the strength of evidence relies additionally on the judgment of the study quality, study design, as well as the statistical measure of uncertainty. Again, a general framework for synthesis or for your meta-analysis is that you want to answer the question of what is the direction of effect? What is the size of effect? And whether the effects are consistent across studies. What meta-analysis can help you to do? If you have several studies included in your systematic review, and they're similar enough, when you put them together in a meta-analysis, you can determine whether an effect exists in a particular direction. It helps you to combine the results quantitatively and obtain a single summary result which is shown as a diamond on the forest plot. You can also use systematic reviews to invest heterogeneity, to examine reasons for different results among studies. Again, very unlikely you will get identical results from studies on a research question. But you will be able to look at why they are different using meta-analysis and related methods. As I mentioned earlier, I really like the definition where meta-analysis is defined as by the analysts of whether the studies are combinable, and here are why. The justifications for combining results. You have to decide whether studies are estimating in whole, or in part a common effect. This is very important, because as I said, very unlikely you will have 2 identical studies. They are similar in some way, and you have to decide if they are similar enough. So when to do a meta-analysis? When more than one study has estimated a treatment effect or association. That means when you have 2 or more studies that have estimated the same treatment effect or association. And when the differences in study characteristics are unlikely to affect the treatment effect. Again, as I said, if the study characteristics, let's say, studies conducted in older participants are likely to affect the treatment effect, saying that the treatment is less effective in older adults, then perhaps it's not a good idea to combine the studies done in older adults with the studies done in younger adults. When the treatment effect has been measured and reported in similar ways, that says that when you have data available, that's when you could do a meta-analysis. There are also cases that you do not want to do a meta-analysis. For example, if the information presented in individual study is really not that great. So a meta-analysis is only as good as the studies in it. You may get a very precise estimate by combining all the studies together. But the combined estimate is worse than the bias study on its own. You have to be aware of reporting biases. That means the published information may be different from what's all out there, including those unpublished information. You don't want to mix apples with oranges, although it's not useful for learning about apples, it's useful for learning about fruit. Again, the studies must address the same question, though the question can and usually must be broader. So when you do a meta-analysis on a set of studies, unlikely that all the studies will be identical. They will be similar. And as a data analyst, you have to decide how similar is similar, and how different is different, and when to do a meta-analysis. I'm going to end this section by showing you a very good example of the importance of synthesizing what we know in an ongoing fashion. And this is a classic example. And there are many more examples that like this. And this is as a cumulative meta-analysis. So here, each line and the circle on the plot is no longer representing the results from one single study. Each line in the circle represents a meta-analysis. And here we have a series of meta-analysis and they were done cumulatively. And this shows us how important it is we synthesize what we know in ongoing fashion. And the topic is now thrombolytic therapy in preventing death, in people who have already had a heart attack. And the way you're going to read this plot, or the accumulated meta-analysis, is like we're adding or throwing a study into the pot. If we had been keeping track of the information, what the meta-analysis results would show, by each time point. So let's take a look. The first study on the thrombolytic therapy in preventing death in people who already had a heart attack, was done in the early 1960s. And the first randomized control trial included 23 participants. It has a point estimate around 0.5. Odds ratio 0.5, favors the treatment. Although the confidence interval is very wide, crossing the null value of 1. And a second analysis was done, again in the early 1960s, so the second study was added to the first study. So combining the two studies together, there were 65 participants. As you can see, the point estimate stays about the same, although the confidence interval gets tighter. So, people kept doing the same experiment or randomized control trials over and over again. By the early 1970s, by the time we had 10 randomized control trials, 2,544 participants were randomized in those 10 trials. It shows that thrombolytic therapy was effective. And the confidence interval, the upper bound of the confidence interval, does not cross the null value. And the p-value is less than 0.1. So by the early 1970s, if we were keeping track of the evidence, we would have known that thrombolytic therapy is effective. Yet, no one were keeping track of the information or the evidence. Investigators kept randomizing patients to thrombolytic therapy versus placebo, or nothing. And look how many more patients were randomized. So by the 1990s, 70 randomized control trials were done with over 48,000 participants. If we were keeping track of the information, we would have known the answer by the early of the 70s. Yet we randomized another 45,000 participants, telling patients, well, we don't know whether thrombolytic therapy is effective. That's why we're randomizing you to thrombolytic therapy or placebo. Imagining the patients who are randomized to placebo therapy, those patients were wasted, because we would have known the answer as early as the 70s. So if you look at all of these estimates, the effect size stays the same, it's just getting more precise. It wasn't until meta-analysis was done that thrombotic therapy was mentioned beneficially in a textbook. So on the right-hand side of this slide you see a grade which shows that whether the textbook or review articles recommended thrombolytic therapy. It was not until meta-analysis was done that thrombolytic therapy was mentioned in the textbook.